Good afternoon, everyone. So, it's my pleasure to introduce today's speaker, Bittu Chahal. So, he did his PhD from IIIT Delhi under Sneha Chobe. So, currently he is doing postdoc at IIT Indore. So, today he'll be speaking on spacing statistics of the Fourier sequence. Bittu, over to you.
Yeah, thank you, sir, for the introduction. So, hello, everyone. First of all, I would like to thank the organizers for the kind invitation to speak in this seminar. So, I am going to speak on the spacing statistics of the Fourier sequence, or simply the distribution of Fourier sequence. So, let me just begin with the outline of my talk. So, first, I will define Fourier sequence and I will discuss some of its properties. And there are many significances of the Fourier sequence, so I will discuss some of them. Then I will discuss the connection of the distribution of the Fourier sequence with the Riemann hypothesis. And then equidistribution modulo 1 of a sequence, and then equidistribution of Fourier sequences and some of its subsequences. And then I will discuss pair correlation measure. So I will let me also recall the history of the Fourier sequence. It is a bit of interesting. So Fourier, so he was a geologist, not a mathematician. So around 1801, he was out of a job, and from 1804 to 1824, in 20 years, he wrote more than 60 articles. And in one article, so that article was of just 4 paragraphs. So he defined and introduced this Fourier sequence and its properties. Like in first paragraph, he discussed this median property that I will discuss in the coming slides. And in second paragraph, he defined the Fourier sequence, and in third paragraph, he gave one particular example. And in fourth paragraph, he said that he is not aware whether this sequence or the properties of this sequence have been pointed out earlier or not. So in 1816, so he didn't give the proof of this median property. So in the same year, Cauchy proved this property and attributed it to Fourier. But in 1802, Harris also constructed the same, or F99, F sub 99, using the median property. So about Harris' work, Fourier and Cauchy were not aware. So in fact, like in his note, Fourier stated that I'm not aware whether this property of fractions has been before pointed out, or whether it may admit of any easy or general demonstration. So because of this, many mathematicians emphasize that the name of the Fourier sequence should be Harris-Fourier sequence. But because of the multitude of articles in the literature, we are bound to use the name Fourier sequence. So let Q be a positive integer, then the Fourier sequence of order Q is the set of irreducible fractions in the unit interval with denominator less than or equal to Q. And mathematically, this set is the collection of fractions A over Q such that A is less than or equal to small q and small q is running up to capital Q, with A and Q are co-prime. For example, F5 is the set of fractions 0 over 1, 1 over 5, 1 over 4, and so on up to 1. The cardinality of the set FQ is given by this asymptotic formula. So to count fractions in FQ, so we need to count small q up to capital Q. And for each q, we need to count A such that A and Q are coprime. And such A's are exactly phi of Q. Phi is Euler phi function. And here this 1 is exactly for the fraction 0. Some of the properties of Fourier sequence. So the fractions gamma I and gamma I plus 1 are consecutive in FQ if and only if AI plus 1 QI minus AI QI plus 1 is 1 and QI plus 1 is strictly bigger than Q. And second one, if gamma I is a fraction in FQ and gamma I minus 1 and gamma I plus 1 are its adjacent fractions, then gamma I is the median of gamma I minus 1 and gamma I plus 1. So this is the median property. So using these two properties, one can construct the Fourier sequence of any order recursively because F1 is simply 0 and 1. So using these two properties, we can construct like recursively sequence of any order. And the Fourier sequence of order Q, they have a correspondence with the set of visible lattice points in the triangle with vertices 0, 0, Q, 0, and Q, Q. So like these, like its connection with visible lattice points. So I will discuss in detail in the coming slides. So in 1894, Hurwitz used Fourier sequence in the rational approximation to irrationals. So in particular, we have Hurwitz theorem, which says that for any irrational number alpha, there are infinitely many coprime integers m and n such that mod of alpha minus m by n is strictly less than 1 upon root 5 n square. And root 5 is best possible. Here we have contradiction example in terms of golden number. And in 1924, Hardy and Littlewood, they used Fourier sequence in the circle method. So like initially, circle method was started by Hardy and Ramanujan, and further it was developed by Hardy and Littlewood. So they developed to study the number of representations of any number n as sum of kth powers of positive integers. In 1934, Ford constructed the Ford circles using Fourier fractions. So Ford circle is circle tangent to x-axis at fraction a over q with the center at a over q comma 1 upon 2q square. Distribution of Fourier sequence. So Fresnel and Landau, so they proved classical result by connecting its distribution with the Riemann hypothesis, and Fresnel proved that Riemann hypothesis is true if and only if the first moment of the displacement of fractions is big O of q raised to half plus epsilon. Here nq is the cardinality of this set fq, and gamma j is the jth fraction in FQ. So, and Landau also proved a correspondence by proving that Riemann hypothesis is true if and only if the second moment is big O of q raised to minus 1 plus epsilon. So after after their classical work, the study of the distribution of Fourier sequence received an overwhelming attention. And there are like, so after their work, there are like other results as well who proved correspondence, like in terms of the distribution of Fourier sequence, like, so there are some results where they consider just like gamma square minus half and gamma q minus 1 over 3. So there are many ways to study the distribution of a sequence, but in here we are interested in the equidistribution and correlation measure. So a sequence xn of real numbers is said to be equidistributed modulo 1 if for every interval, every subinterval I of the unit interval, we have that 1 over n and times cardinality of the terms of the sequence such that the fractional part lies in the interval I is tends to the length of the interval as n tends to infinite. Or in other words, we can say that a sequence is equidistributed if every subinterval of the unit interval has its fair share. So, the study of the equidistribution, started early 20th century when Hermann Weyl laid its foundation, and he connected equidistribution with the exponential sum by proving the following criteria. He proved that sequence is equidistributed or uniformly distributed, modulo 1, if and only if the average of this exponential sum tends to 0 as n tends to infinite for all non-zero integers. So in particular, this equidistribution of a sequence is a qualitative concept. So it does not provide the quantity of the distribution. So it is natural to have the corresponding quantitative concept. And so we can say that there may be two sequence. One is with good equidistribution and one is with bad distribution. So in a vague sense, I will describe like what is good and what is bad. So for that, we study the discrepancy of a sequence, and discrepancy is the quantity that measure the deviation of a sequence from the perfectly uniform distribution. So let xn be a sequence of real numbers modulo 1 and a be the number of terms of the sequence xn for which fractional part lies in this particular interval alpha to beta, and the number dn, which is the supremum of this quantity, is called the discrepancy of the sequence. So here we can say that that this is like measuring the quantity from a perfectly uniform distribution. And since it's a quantitative concept of uniform distribution, so there should be some relation in between equidistribution and discrepancy. So for that, we have the following result, which says that the sequence xn is uniformly distributed modulo 1 if and only if dn tends to 0 as n tends to infinity. So here, there may be two sequences which for which this quantity or discrepancy tends to 0 very slowly. So that means that has a bad equidistribution, and we may have some sequence which is tending to 0 fast or very fast. So we can say that has a good equidistribution. So discrepancy of the classical Fourier sequence, for that, Neville in 1949 proved that discrepancy is big of log Q upon Q. And his estimate was improved by Nederator in 1973, and he proved that the lower bound for the discrepancy and upper bound are 1 upon q up to some constant. So in here in the first bound, so he didn't utilize the cancellation coming from Mobius sum, since in Fourier fractions we have that a and q are co-prime, and by detecting that co-primality condition with the Mobius sum, so and so after some calculation, so we can utilize the cancellation for Mobius sum, and that idea or that trick used by Nederator, so to improve this result and to get rid of this term log Q. And Dress in 99 proved a remarkable result by proving that discrepancy is exactly 1 upon Q. So discrepancy of the Fourier sequence or with some conditions on denominators, or discrepancy of the subsequence of Fourier sequence. So Alkane, Ledon, Vazetu, and Zarescu, they studied the discrepancy of fractions when denominators are B free and they are in some arithmetic progression. And they also studied the discrepancy of the Fourier fractions when denominators lies in the set of there are some k congruence conditions, and denominator lies in that set or union of those sets. And in 2018, Ledon studied the discrepancy of the Fourier sequence so in an arbitrary subinterval. So he considered when fractions, so not in unit interval 0 to 1, but he considered any arbitrary subinterval of this interval, and fractions lies in that particular interval. And also when denominator in some arithmetic progression. Now, Fourier fractions and visible lattice points. So a point AB is called visible from the origin if there is no other point of Z2 on the straight line joining origin and that point AB. In other words, we can say that a point is visible from origin through straight lines if A and B are co-prime. So Fourier sequence of order Q can be viewed in terms of visible lattice points. That means that FQ is the set of fractions A over Q such that AQ is visible from origin through straight lines. So here visibility of points, so instead of straight lines we can consider other curves like parabola y is equal to x square, y is equal to x cube, or general y is equal to x raised to k, or in more generality we can consider visibility through polynomial curves. So what is that? Let me first define it. So let C be a n-tuple, be a fixed vector such that Cn is non-zero and Ci's are positive and Ci's are co-prime as well. And let Fc is the collection of those polynomial curves where P, this polynomial is defined like this. So a point AB is called Fc visible if there is no other lattice point on the polynomial curve y is equal to R PCX joining the origin and the point AB. So now instead of straight lines, we are considering polynomial curves. So the density of these polynomial curves was recently studied by Sneha and her collaborators. So let us denote the set of all Fc visible points in N2 by Vc. And now we define polynomial Fourier sequence as, so FQ is the set of fractions such that the point AQ is visible through polynomial curves. So instead of straight lines, we are now taking points to be, so that the point AQ should be visible through polynomial curves. So this defined Fourier fraction in terms of visible lattice point along polynomial curves. So here, to study the distribution of this set F sub QV is a bit of difficult problem, because for this condition, for the visibility, we do not have any arithmetic in terms of arithmetic conditions. So as in the case of straight lines, we have arithmetic condition that GCD of A and Q is 1. If AQ is visible through straight line, so we can translate to in GCD condition. So, but here that arithmetic, such type of arithmetic condition is missing. So that's why it's a bit of difficult problem. So for that, we consider a subset of this set. And this is defined like this: f sub qp is the set of fractions a over q such that GCD of p at a and q is 1. So it's easy to see that this set is a subset of this f sub qv. So now for the distribution of this sequence, we prove that the discrepancy is less log q raised to j upon q and greater 1 upon q. And here j is the number of distinct irreducible factors of the polynomial px. So here as well, like for the upper bound, we are getting this log term, and this term we are getting because we couldn't utilize the cancellation from obvious, as you remember in the case of Neville. So and because so here when we estimate this discrepancy, so we need to count the solutions of this polynomial congruence modulo some d or some modulo. So when we are counting, so for complete interval, suppose like we have interval up to d and we are counting solution modulo d. So those we are fine, but for incomplete intervals, like it's not easy to get exact or closed form formula. So for that we need to like take bound for those incomplete interval. And so because of that, if we are taking bound, so then we lose on the Mobius. And as soon as we lose on the Mobius, so we get here log term. But like here, there are chances of like improvement. It should be 1 upon q, like best possible. So as q tends to infinite, so discrepancy tends to 0, and we can conclude that the Faraday sequence f sub qp is equidistributed modulo 1. So we also like establish a closed form formula for the corresponding Weyl sum. So let px be a polynomial in zx, then the corresponding Weyl sum we can write in this form. So like for a general polynomial, so it's like here we have a closed form formula, but it's not like neat and clean. So for particular polynomials, we can write like this closed form formula in a very neat and clean form. So that I will discuss that result in coming slides. So because of that, for a general polynomial, in the correlation result, we couldn't get an exact formula for the pair correlation measure. So now the discrepancy or equidistribution, so they measure the distribution of a sequence on a fixed level or on a fixed scale. So on a fixed, in other words, we can say on a fixed interval. So, but to get finer distribution or local distribution, such as like the randomness or or the periodic property of the sequence, like we study gap distribution or correlation measure. Let f be a finite set of cardinality n in the unit interval 0 to 1. The pair correlation measure R sub f of I of a bounded set I is defined as 1 upon n into the cardinality of the tuples in the set f cross f such that they are distinct and their difference lies in this particular interval. So if on taking the limit of this set, if that limit exists, then we say that the limiting pair correlation measure exists, and let us denote it by R of I. And if this R of I we can write in this integration form, then this G is called the limiting pair correlation function of the sequence Fn. And if G is identically equal to 1, then the pair correlation is said to be Poissonian. So initially, the correlation was the study of correlation. So initially was studied in like in physics in order to understand the spectra of high energies, or like simply the distribution of particles. And Montgomery is the first person who studied it from mathematical point of view, and he studied for the zeros of the Riemann zeta function. So he conjectured that for any beta positive, the pair correlation measure is given by this asymptotic formula, or in other words, we can say that the pair correlation function of the zeros of the Riemann zeta function is 1 minus sine pi u upon pi u raised to 2. And to conjecture this, he considered this like this weighted exponential sum. And for this exponential sum, assuming Riemann hypothesis, and when alpha is greater than equal to 0 and strictly less than 1, he proved that f alpha is given by this asymptotic formula. And for other values of alpha, he conjectured that f alpha is of order 1. And using this f, he conjectured the pair correlation function. And the pair correlation of Faraday sequence was studied by Boca and Zarescu. So they proved that pair correlation measure of the classical Faraday sequence exists, and the pair correlation function is given by this closed form formula. And also they proved that as lambda tends to infinite, this function behave like this function become constant and behaves identically equal to 1. So this is not exactly equal to 1, but for large values of lambda, this behaves as 1. So we can say that like this tries to become Poissonian. Otherwise, like for small values of lambda, it has like graph of this, like it has a repulsion, and it is not 1, as we can see. So for that, like for exact that how it is behaving, so we plot graph, and we will see that the behavior of this function. And now pair correlation of the Faraday sequence with some congruence conditions on denominators. So Xiong and Zarescu, they studied the pair correlation of Faraday fractions when denominators are co-prime to BQ. So BQ is a sequence of is an increasing sequence of positive integers such that BQ1 divides BQ2. So in Boca and Siskaki, they studied the pair correlation of Faraday fractions with when denominators are in some arithmetic progression, and also they have some coprimality condition. And myself with Sneha, we studied the pair correlation of Faraday fractions when denominators are square free. And recently, Maisilu extend our result by examining the pair correlation of Faraday fractions in a short interval when denominators are square free and lie in an arithmetic progression. Now, pair correlation measure of polynomial Faraday sequence. So let Px be a polynomial with non-zero discriminant. So we prove that the lim sup of the pair correlation measure is finite, and it is bounded by this like this identity. So here beta p is the Euler product, and f sub p is the like number of the solutions of this polynomial congruence modulo p. So here, as I have discussed the Weyl sum for a general polynomial. So to prove or to estimate the pair correlation measure, so what we do, so we change our problem to estimate the exponential sum, or in particular Weyl sum. Then things depend that how neatly or how nicely we can estimate, or we can get a closed form formula for that exponential sum. But for a general polynomial, it's a bit of difficult task to have. So for that, at some point, we have to take bounds, or yeah, and that's why we are just getting we were just able to prove that this limb soup is finite, and it has this bound. But for particular polynomial px is equal to x into x plus 1, we prove that the pair correlation measure exists, and the pair correlation function given by this closed form formula. So it is not that clean that we have for the classical Ferri sequence, but we have a closed form formula. And here hm is given by this summation, and this summation runs over the positive divisors of m. So let me give you the idea of the proof. Oh, but before that, let me describe the behavior of these pair correlation functions. So for that, this the top one graph is for the pair correlation function of the classical Ferri sequence, and the second from upper side is for the polynomial Ferri sequence for the particular polynomial px is equal to x into x plus 1, and this y is equal to 1 is for the z is equal to 1, which shows the Poissonian pair correlation for the sequence which has Poissonian pair correlation. And this one is for the zeros of the Riemann zeta function. So we can see that all three, as lambda tends to infinite, so they are trying to tend to 1, or they are becoming constant. So but here, so near to 0, the graph of pair correlation function, they have support in this tiny interval. And because of that, they are having that much of strong repulsion. And that repulsion, we do not have in the graph of the pair correlation function of Riemann zeta function. So here, since it is 0, so we can conclude that the fractions with the very fractions they have with a small gap are very rare. So we cannot say that there are no fractions with a small gap. There are, but they are very rare. So to prove the pair correlation measure, we need to estimate or we need to count
Bittu,
the pulse.
Bittu,
Yes.
can I ask one question? The
Yeah.
graph, you can you go back? The graph mentioned by green color. So what
Mhm.
is that?
So yeah, this is for the bound of that we have for a general polynomial. This is just like a bound, a rough graph.
Okay. So
Yeah.
that is not approaching to one as lambda
So yeah, so
tends.
actually it will approach, but since it's a it's a bound, so it
Okay.
will approach a little bit later.
Okay,
But
I see.
that yeah, that we didn't include here because it was for when lambda is too large, because
Okay.
yeah, in that bound that constant can be yeah, too large, so that's why it is going a bit of high.
Okay. Okay. Okay.
Yeah.
Okay. Yeah. Thank you.
So to prove the pair correlation measure, we need to count the tuples in the set f sub qp such that they are distinct, and their gap lies in this particular interval. So let h be any continuously differentiable function with the support lies in this particular, so in that particular interval that we want that their gap should lie. And we define hy as the summation of this function h, and also we define f sub qp is equal to summation of this small h. And here gamma 1 and gamma 2 are in f sub qp, and gamma 1 and gamma 2 are disjoint. So using this expression for h, we can express this summation in this form. So here, using the fact that support of s lies in this particular interval, we can leave this condition that gamma 1 and gamma 2 are disjoint, because here if they are equal and n can be 0 as well, so this term this inner expression of the function h will become 0, and it will automatically give 0 because of this support condition. So here we can observe that H is Z periodic. So we can write its Fourier expansion. So by writing Fourier expansion and inserting in the first summation, we can change this problem into estimating the exponential sum. So now like our counting. So one more thing here, so what we will do at the end, we will like approximate the characteristic function of this particular interval 0 to lambda with the smooth functions, and by approximating that we can say that this s sub qp exactly becomes this set where we are counting those tuples with this condition. So now our problem of counting tuples has been changed to estimate the exponential sum or corresponding Weyl sum. So for the polynomial px is equal to x into x plus 1, we prove a closed form formula which is like which is a bit of like yeah, lengthy, but it's a little bit neat because in that one for a journal polynomial, so we have that condition or that congruence condition that p of x is congruent to 0 some mod d. But here for this particular polynomial we can using Dirichlet characters we can change that condition into Mobius sum and Euler sum. And because of that we can further like estimate this. So like now inserting this expression into one, and also like after inserting, so because we need to take care of this Fourier coefficient as well, here cr is crr Fourier coefficient. So in the second term here we have like this exponential sum and it depends on r as well. So when we will estimate this Fourier coefficient, so we will use Poisson summation formula, but because of this like exponential term which has r, so we need a weighted version. So we approved a weightage version for Poisson summation formula, and using that we can change our that expression s sub qp can be changed into this. So in between there are like yeah few things and few like change of variable and those. So after doing like those things we can express our sqp in this form. So now we will use the the support of this function h. So using that we can say that this expression should be in between 0 and lambda. So and this implies that delta n d1 d3, so they are not running up to q, but they are running just up to a constant. So using that fact, now our problem has been changed to estimate like or to count lattice point with some weight and with some extra coprimality conditions. So for that, because here h is a smooth function, so it's a smooth weight, and is S1 is a modified set of this S with a little bit. In S1 we have 2 3 more conditions, more coprimality conditions. So to handle this sum, we prove the following result for lattice point count problem. And so for that we have proved that an asymptotic formula where m of r1 and r2 are like they are finite and depends on the prime divisors of r1 and r2, and e is given by is the error term and given by this. So after like inserting this 2 into this summation, and then yeah, at the end using the approximation of characteristic functions with the smooth functions, we can prove the estimate for the pair correlation measure. And yeah, one more thing, because here we have error term as well. So as we will take q tends to infinite, so error term is this is of small order in comparison to like q square, so it will tends to 0. So we also study fractions with prime denominators. So Xiong and Zarescu, they studied the pair correlation of Faraday fractions with prime denominators. And they proved that pair correlation is Poissonian. That means the pair correlation function is constant and identically equal to 1. And they also studied when denominators are product of 2 distinct primes. So, and in that case as well, pair correlation function is identically equal to 1. That means it behaves as a Poissonian. So Maisy Lu, so he extend their result by taking denominators to be a product of k distinct primes. And he proved the pair correlation result. So now for polynomial Fourier sequence, when denominators are prime, so let q be a integer and bq be any subset of primes. So we define m sub bqp as a set of fractions such that p is in bq. So we are not restricting to all primes, but here we can take bq to be a set of all primes. So but we prove a more general result. So we prove that pair correlation function of this sequence exists and is Poissonian if and only if we have this condition on the set BQ. That means the second moment of the primes in BQ is small of the square of the cardinality of this set. So now by taking BQ to be like particular set, or to be a set of all primes up to q, so we can like verify that for all primes this condition satisfied, and can say that the set of polynomial Fourier sequence when denominators are prime has Poissonian pair correlation. And also we considered like when denominators are prime k-tuple. So let a1, a2 and ak be distinct positive integers. So a prime p is said to be a prime k-tuple if p plus a1, p plus a2 and so on up to p plus ak are all prime. And also we studied when like denominators are Piasecki prime. So let C be a fixed real number between 1 and 2. A prime P is said to be Piasecki prime if it is of the form, if it is equal to greatest integer of n raised to c. So, and also we considered when denominators are Sen primes. So a prime is Sen prime if p plus 2 is a product of at most 2 primes. So by taking bq Q1 and BQ2 to be a set of Piasecki Sapro prime and Sen prime respectively, then their corresponding sequence have Poissonian pair correlation. And for the set of prime k tuples under the Hardy-Littlewood prime k tuple conjecture, we proved that the pair correlation of the corresponding sequence is also Poissonian. And we also studied when denominators are prime with restricted digits. So let Q be a positive integer. So for any choice of D in this set, let A be a set of positive integers with digital restrictions in base Q. So, and a prime P is said to be a prime with restricted digit if P is in A. So now let BQ be the set of primes that are less than or equal to Q and with restricted digits. So we have proved that the pair correlation of the corresponding sequence exists and is Poissonian. So like to prove these results, so we need to verify this condition for each set BQ. So like we can take any set if that particular set of prime numbers satisfy this condition. So we can say that the corresponding sequence has Poissonian pair correlation. Thank you for your attention.
Okay, thank you, Bittu, for nice talk. So, if you have any questions or comments, please feel free to ask. Okay, so Bittu, I have one question. Like, can you go to that few slides back? So
Yep.
BQ, mm,
This one or
no, a little back. Yeah. So here BQ is for BQ a subset of prime numbers.
subset of
Okay.
primes? Yes.
Okay. So it can be any subset. Like for example, it can be any arithmetic progression like
Yeah, exactly.
like okay. Okay.
Yes. Yeah, it is any subset of primes. And if we have this condition, so we have this result.
Okay.
And
So
it's a if, yeah, if and only if in both cases.
okay. So have you tried like for all those primes they are in like some particular arithmetic progression?
When primes in arithmetic progression, so like yeah, we have not tried, but we can
Mhm.
get from this result. So I'm not
Okay.
sure like if that is done or not. I think that is not done. Yeah.
Okay. Mhm. Mm. Okay. So one more thing. Can you
Yeah.
go back to the page number 6? So there is yeah. So Riemann hypothesis is equivalent to this two bound. So now my question is that whether the higher power of has been higher power of delta J, and for that also bound has been studied or not. Like have you
So higher power,
of
like
delta J?
as much as I know, so like I know when like gamma z cube, so not in this form, just when delta j is gamma z raised to cube and some minus some constant 1 over 2 or 1 over 3. Yeah,
Okay.
has been done. But I think journal delta raised to j, I'm not sure.
Okay. So
Yeah, I don't
because
remember.
delta J, modulus of delta J, the that sum has been studied, square also had been studied. So that's
Yeah.
why I'm just curious to know that whether delta J cube or any fourth power, there also you get something, some bound is
Yeah,
equivalent to.
exactly. So, like, yeah, I am not exactly sure, but yeah, I don't remember.
Okay.
Like,
Okay.
so yeah, like, yeah, I will have to, yeah, one search the literature
Oh, okay.
then only because, like, yeah, there are like after their results, so there are like multiple paper games on similar things.
Okay. So If any questions, any other questions?
Yeah, Bittu, hello.
Yeah,
I had a
hello, sir.
question. Nice talk. So about the BQ, which again Vivek was asking that slide. So BQ does not have
BQ.
to, as Q varies, we have no restriction. BQ can just randomly vary, is it? Or there should be a subset and it should be increasing or something like that.
So here BQ. So BQ is any, like we can take any subset.
At any stage, for any different Q, you can have different subset, right?
Any, yeah, it may be different, or yeah, we may fix as well. Like
Okay.
it
So
may, like
even if
yeah, it may
it,
increase as
mhm. Okay. And
well. But
then
here, like primes are up to Q.
the primes
Yeah,
are up because they're what's the
yeah,
word?
primes are up to Q.
Definitely some subsets of those primes up to Q.
Yeah, some
No, I
subsets.
was just curious. So sorry, because I have not thought it through. But if for primes itself, when it was Poissonian, so any subset of primes is not by default Poissonian? Just asking a stupid
By
question.
default, oh no. So like yeah, so it's like a problem that if a sequence is has like Poissonian pair correlation, so its subsequence may not have
I see.
Poissonian. So like even like we cannot say if a sequence is equidistributed, so we may find even its subsequence doesn't have even like equidistributed. So like
Mhm.
there is a, like I don't remember paper, but yeah, some examples
That
were
would be
considered
example.
where sequence is equidistributed. But so in that paper, so one example was considered of like the subsequence of that particular sequence, which is not equidistributed. So like in that
Okay.
sense,
Okay.
yeah. So yeah, we may have example where like subsequence even, yeah, if not
Sure.
equidistributed, so they may have like a
But
non-Poissonian.
what was this capital P of A in this? Let me
Yeah.
see.
So capital P is the polynomial that I have defined.
Oh, I see. So this is
Yeah.
for a fixed polynomial.
Yeah.
Your
Polynomial is
favorite polynomial.
fixed. Yes. Polynomial
X
is.
into X plus 1, right?
Yes. So no, it's like general polynomial.
General polynomial. But it
Yes.
is fixed.
Yeah, it is fixed
Yeah,
of
it's
some like fixed
confusing.
degree.
But if it was just P of X equal to X, then it would be
Then
true
yeah,
for
it's
all
a classical
classical. I
classical
see.
Fourier sequence with prime
Okay,
degree.
okay. Sorry. I get it. Thank you. Thank you.
Yeah.
Thank you. Yeah.
Yeah. Thank you, sir.
Okay. So if there are no questions, let us thank Bittu once again.